Well, it has to be said that actually the word towards probably should happen as the first word here, but that would just be getting too silly. I'm not going to give you the solutions to all this problem. I'm really just going to raise a whole bunch of technological developments that I think kind of fit together to potentially help solve these sorts of problems in future. But it's the grouping here. We'll talk about information flow control, a little bit about programming languages, a bit about operating systems, and the data sovereignty tracking is the long-term goal of this. The motivation, I kind of looked at something which was a smaller version of this in my talk last year, where we're looking at how you could label code repositories in ways that could carry metadata of the type that you might want for Indigenous data sovereignty. Really what I'm looking at here is trying to connect the sort of security academic research that I've done through my career to the human level concerns that typically sit above the really technically detailed stuff that I'm looking at. So most of my actual research has been looking at operating system security, really low level stuff. But I'm keen to see how you connect the sort of human level concerns into those sorts of technologies. And that's really what I'm seeing, how these technologies might fit together going forwards. So the aim is sort of how you can get ways to help enrich software code with easy ways of having metadata travel through that code. And the particular objective would be to support all types of data sovereignty tracking. As this disclaimer, I'm not claiming authority when it comes to things like Indigenous data sovereignty. I had the honor to be involved in a project run from CIFTI, the Veracity project, that did have experts that could bring that actual Indigenous data sovereignty perspective to the table. That project is now kind of on a pilot light, and hopefully we get to kind of make that, I don't know, with so much flammable change around right now, maybe that's the wrong analogy to use, the pilot light. Could be destructive, but hopefully we'll get that project kind of back into action and doing more work in future. Work on some very big objectives there, but data sovereignty tracking was part of that. So at the moment, this is not something which is co-design. This is more taking work that has been in where I've been in terms of the academic work and looking at the connections to this human level concern. So I think there's some promising approaches for systematic security, but a lot of these technologies aren't integrated yet. So looking at this particular picture here, this is kind of, interesting. It's also a figure that I got ChatGPT to make, just out of interest. I was like, could I prompt it to give me a figure? In this case, I got it to do the TIX PGF LaTeX code rather than actually making a figure, but it actually did a pretty reasonable job on the prompt. So I went with it also as that point. What I'm showing here is like a multi-tier architecture where you have your PHP application doing some website thing, you've got a relational database sitting behind it, and you've got an operating system that sits behind that. I mean, there's other components you could bring in, but 3 was enough. Often, not always, but often, you get these software systems where you might have multiple users of that application software at the top layer. So you have 3 users, app users 1, 2, and 3 in this case. Even by the time you started hitting the relational database that's doing the storage of the data from your PHP application, that gets compressed down to a single user. The PHP application has a user, it accesses the database, and you've totally lost the fact that there were these 3 application users at the top level. That process repeats itself when often, not always, but often the relational database system talks to the operating system, and it too, the relational database has a notion of different users in its database management, but the operating system doesn't see that. So at each level of this picture, you're kind of getting this opaque representation of the concerns of the layer above. And I don't think we really need to be like that. Software started like that because we had technical constraints on the number of things we could use. I don't think we're in that place anymore, so I'm interested to see that sort of be freed up. This slide gives the sort of text that relates to the figure that I just showed, so to skip through it, I'm just saying that, yeah, we have this problem that you lose semantics between the different layers of these multi-layered systems. And ideally, we would like all of those tiers to understand user data links. If you want something from the ancient history realm, back in 2014, I had a very, very talented postdoc who's now actually faculty in the department, running a project where we tried to kind of get a web application and actually see how we could track this metadata through that system. In our case, we were using a sort of file-based wiki application, and we did have some success in getting the SE Linux security framework tracking some of the permissions right across those different tiers. It wasn't the easiest project, which again, here you need the friction to be low if this is actually going to work in practice. So another kind of aspect where I think we may see changes that could be useful for labeling represents access control. It's very typical for most systems to have the top picture in blue, which is discretionary access control, where owners of resources get to set the permissions on the resources that they create. And then that means other users, step 2, you can open up access to other people to access your data. That's in contrast to environments which have mandatory access control, where you have the kind of security policy and labels sitting completely in the midst of the users, the subjects on one side and the resources they're accessing on the other. Often mandatory access control is more secure in the sense that it gives you a higher assurance as to what the behavior of your system is, but it's often harder to work with. And so again, this is another figure that ChatGPT did for me, again with that just that experiment of whether it could take this sort of information and give us a graphical view of it. It's usually just been the case that systems have developed with this discretionary access control. What I'm interested in is where you take the mandatory access control ideas and the security that it can provide with this systematic labeling, but you can elevate it to a level that makes it more useful. And one of the technologies that can help with that is beg your pardon, I'm going to talk a little bit more about mandatory access control first, so I got my slide ordering wrong. What you do with mandatory access control is you have labels that you apply to the data and labels that you apply to the users of that data. And so the labels will be the typical intelligence organization type things, public, secret, top secret, that kind of stuff. And then you've got some very easy rules that you can apply systematically to all accesses to that data, that you're not allowed to write top secret information that you can see down to a lower level. That would be declassifying the information. That's an unusual operation, so normally you can't do that. And you can't read things that are above your security classification. So you've got that kind of strict hierarchy. Easy to apply these rules and to apply them systematically across the data accesses that occur in a system. Often they're part of the operating system, so that kind of is where they kind of stick in there. But you get this consistent application, which is good. The difficulty is that those labels often don't apply to something like data sovereignty, which is multifaceted and requires a much more complicated form of labeling. But information flow control is a technology that builds on mandatory access control to actually try to help this tracking of metadata through systems. I would say it's less implemented than mandatory access control, and that's pretty rare anyway. So we're in quite niche technology in terms of the space that we're in here. But I'm keen to see where data sovereignty considerations can be built into the metadata that information flow control is actually tracking. And then you can get these information flow control engines to enforce the security rules that you want enforced in a kind of consistent way. You can build that into your normal software, but ideally we'd like to make it as easy as possible. And that's where I'm interested to see what ways can software engineering change to make using this kind of security more straightforward. One area that I'm particularly interested in, and I think there's an emergence of quite a lot of development in this space, although it's low level and a long distance from indigenous data sovereignty at the moment, are capability systems. Here, a capability is an embodied permission to do something. Often capability systems are sitting really low down in the technology stack, but they allow you to do some, again, thorough security practice. And so I'd just like to really quickly skim through a couple of places that I've shown here in this list, and I'll go through on the next slides, where we're seeing capability systems that can enforce access control in potentially interesting ways. One of the aspects is in programming languages. And so what you can do with programming languages, some programming languages have extensions within the language that allow you to deal with these sorts of security labeling and considerations, potentially. Or you've got languages that are dedicated and actually support information flow out of the box. The problem is they're all pretty obscure languages. And so an example of that, we have some things which is sort of brain bending that we don't do this systematically in computer science. Ideally, you have kind of, I'm just giving you an example of one of the sort of basic starting points here. Programming language is actually encoding types of units into what they do. Again, this is a historic throwback, I would argue, that in most cases when you've got a programming language and you say, what type is this variable in my programming language, you're kind of thinking about what the machine needs. Is it 8 bits long? Is it 64 bits? We're hearing about, the float 64 stuff in GPUs this morning in terms of the keynote talk. It's machine-oriented considerations. But human semantics are really important as well. And examples here are things like units of measurement. It's been the case that the 1998 Mars Climate Orbiter was lost because of a difference in units of measurement. Exactly the same machine type, but in one case it was an imperial unit, in one case it was a metric unit. They don't mix very well together. There's no reason we can't extend programming languages to actually understand that those are different types of data, not in the machine sense, but in the semantics. And indeed, languages like F# and Ada actually do support this idea of having units of measurement. So they will refuse to build software that would mix an imperial unit being multiplied with a metric unit if you don't actually say, I realize I'm doing this. It's actually a type conversion. Other languages which are less niche than F# and Ada, Rust, Scala, and Haskell have libraries that can extend the languages to do this kind of stuff, but we're still talking really obscure languages here, which is the problem. We've got this great technology, but it's just not where we need it to be in terms of making it easy to use. I'm all for functional programming, but that's more of a kind of academic sell. There are lots of other languages that more generally support the idea of annotating stuff, so having annotations in the language. Now that's the issue here, is that while annotations in programming languages, in here, I'll put the obscure languages first, but things like Java and C# and Kotlin are languages which are a little bit more mainstream. I mean, they're not necessarily going to cover everything, but they are languages that will support this idea of code annotation. And that just essentially means you've got some unit that you can type into the syntax of your programming language that the language system will read and it will carry, but doesn't actually really react to, usually. But it's a tag that you can have other tooling then react to. So it's a useful extra piece of metadata to sit flowing through your code. The main problem with this is that at the moment, annotations are typically not used for security enforcement. So I mean, they could be potentially, but it's not something which I've seen done in a mainstream way. So they're setting us up for being able to support information flow control, but they don't come with information flow control engines that react to those annotations. There are programming languages that actually support information flow control more directly. But again, these things, we back into the obscure language problem. So I mean, let me know if otherwise. I've certainly never used any of these languages. I mean, I studied GIF, but I've not used it in like a mainstream project. I think that probably nobody here has used any of those languages in earnest because they're all very much on the obscure side of things. What's interesting is if you want to have a really firm description of the security of your system, you want to appeal to mathematical proof. And so the first, what I've called theory-oriented languages here, they're often not even the types of languages you would use to write code to run. They're often ways that you would describe a specification that you want mathematically proven. But in my kind of long-term vision, I would like it to be the case that the strength of that mathematical verification could be brought to more accessible programming languages. I mean, clearly that's something computer science as a whole should be trying to do. We don't want to have the case that something desirable like information flow control is unattainable because we only have it implemented in obscure mathematical specification languages. And I do think there's progress, but we're not quite there yet. A more pragmatic example is this system GIF, which took Java and extended that language in two ways. They modified the Java syntax and engine to be able to annotate the concerns that you have in information flow control, what you want to track about information moving through your system, and they also then changed the whole Java runtime, the JVM, the actual runtime engine, to enforce aspects of information flow control. So it's a project that's actively maintained and it has been used in projects, but it's still pretty much on the academic side of things. It's still fairly obscure. Their aim is not take a general Java program and then turn it into one that has information flow control. Their aim is that you would write your software in this environment to begin with. Two other forms of capability systems that I'll cover before hopefully getting some time left for questions. One which is really interesting to me is starting to see capability support appear in CPUs themselves. And this is really lifting, again, the assurance of the way that your software works. It's quite different from the other examples I've shown so far. So this is largely a Cambridge-driven project. The capability hardware enhanced RISC instructions. I mean, they were just trying to make a nice sounding abbreviation. So I think they have agreed that the actual expansion of the abbreviation is a bit awkward. But essentially, they have shown that you can take CPU designs. One of the problems you get is memory safety. We've seen that come up in, for example, the executive orders from the previous administration in the US, saying that we want memory safety in terms of government code. I think the current situation might be different, but let's not go there. This kind of world is where you have, what you're trying to do is build a CPU where the hardware itself means that you don't have the problem with memory safety that a lot of the languages that a lot of software implemented in otherwise causes. So the C language, you've got pointers in that language. They can point anywhere. You can sort of shoot yourself in the foot with respect to the way you can write code. These CPU extensions work against that. And so they actually give you a way where the CPU enforces properties directly, such as when you have this idea of capabilities, you take the idea of a pointer to a memory location, all pointers become capabilities, and capabilities include not only a place you're pointing to, but a bound within you can change the extent to which you can change where that pointer points to, and it can also carry some extra permissions. So in terms of taking typical C code, this is the case where they're trying to take existing operating system code, which is filled with bugs and memory leaks and all sorts of problems, and they're trying to say, you can, with minimal effort, port your operating system to actually run on this type of CPU, and they're showing it working for BSD, and Linux is kind of nearly there. Well, I think bits of Linux are there for sure. They're showing that you can kind of bring this forwards, and then you get these much stronger guarantees about the safety of your system. Like it doesn't fix all security problems, but it fixes a lot of the big ones. And so what interests me it's a very elegant system. It's got this kind of ability to have these constraints. Like once you've got a capability, it's enforced that you can't forge capabilities. Essentially, if you try to touch them with code, they get destroyed. They're not capabilities anymore. You've got this ability to allocate someone access to an area of memory, and then they can go and make other capabilities, but they can only ever make capabilities to smaller ranges of memory. So you get this really nice hierarchical property in terms of the safety of access. But when it comes to the main topic of this talk, they can also be extended to include other attributes. And so here too, this is where I see the potential to have the more human level concerns of things like data sovereignty actually being carried by this type of metadata through the code. This type of work has actually been really built. So there's an ARM in the in the UK, ARM actually built some machines called Morello that are physical hardware that actually run these modified CPUs. So they really exist, and they actually run real software. The last one is probably the most obscure, is looking at doing formally verified operating systems and where we can potentially connect the human level concerns into a very different way of engineering operating systems. So really, you need to fix the operating system you're running on before you can build secure applications. Because it's all nice to have secure implemented applications, but if you've got vulnerabilities in your operating system, it can undermine whatever security your application has. And we don't really do a great job of building generally widely available secure operating systems, which you see from the number of times you need to apply security updates. One of the developments that was done at UNSW in a world first back around 2009, it depends on the timing of when you look at the different stages of the mathematical work that they were doing, they verified this microkernel that they'd built called SEL4, which is an operating system that probably nobody much has heard of. Has anyone heard of SEL4? No, okay, so it's a series of these microkernels. SEL4 is now being deployed into things like drones, and let's not talk about why, but I mean, it works, but like there is that software going into those places. The same group built another related microkernel on the L4 series, which if you've got like one of these Macs, you are running that operating system, but you're running it on your security coprocessor. So they can't afford to have your security processor mess up security because that's kind of like the root of trust for the rest of your system. So yeah, they're actually running one of the L4 series microkernels. But it means it's pretty obscure, because if you've not even heard of it and you don't realize there's a thing in your machine that's running this operating system, there's a couple of things. It means it's probably small, it's probably niche, and the point here is that it's exceptionally difficult to build on. So there have been large organizations that have tried to build big things in SEL4 or build things above SEL4, and those projects, they haven't materialized. It's 2025. These sorts of developments happened a long time ago. But what we're starting to see, and there's a couple of things, including some startup companies that may be based in New Zealand, that are moving towards actually building new software stacks that are now available on this kind of infrastructure. And I think that that's really interesting, because all of the security of SEL4 is built with capabilities. The whole thing is capabilities. It's done as a software system, but it's a software system that's mathematically verified. So I'm kind of trying to stretch as quickly as it's possible to build small, useful components in this formally verified system, this kind of very, very low level capability connected to the sort of higher level concerns that you might want to have when dealing with something like Indigenous data sovereignty. And again, it doesn't solve the problem, but it gives you a very different level of assurance in the actual protection these systems provide. So in conclusion, it's totally fine and good to engineer handling data sovereignty into your applications. At the application level, that's fine. This is good. I'm absolutely not arguing against that. We have some good emerging data flow and workflow languages that might allow you to track things like this metadata through those systems increasingly easily. There are standards for tracking provenance, and these are good tools that you can use if you want to actually keep track of metadata traveling through your system. But my pitch here, although I'm on the rather obscure end and the sort of 10 years time end of this pitch, is that computing should support concerns like data sovereignty just better. What I mean by that is that the assurances we should get should be higher from the quality of the technologies that we're using to actually build them up. And so I think it's going to be possible, and there are emerging technologies that bring us closer to integrating information flow control and security, not only in the kind of typical integrity and confidentiality sort of notion that's used, but also allows us to have rigorous verification of some human level considerations, things like handling in sort of data sovereignty. So I'll stop there, ask if there are any questions, and obviously this is an open invitation. I haven't given you any answers, so if anyone else wants to come up with the answers, that'd be great, and I'd love to join you in the mission or vice versa.
Great. Thank you, David. Any questions? Yeah.
Make it tough.
No, it's not going to be tough. Can you just flip back to a couple of your earlier slides, I think?
Yeah.
Can you just elaborate on why Scala? Because you had it both as...
Which was?
You had it both as an annotation, but also...
Oh, Scala. Yeah.
And also as unit of measurement.
Where are we? So, yeah. Yes, that's right. I mean, Scala is a great language, but again, I mean, how many people have used it? That's the problem. I mean, it exists in places that have high impact. So, like, Twitter uses it, or Twitter's not Twitter anymore. But you know, there you go. That shows my age. I mean, there's a whole bunch of things which did high-performance message passing, where Scala is a really, really good language to use. I mean, as a teacher, I'd say it's also a really nice language. I mean, I've used it for really sort of simple educational tasks. But that's the problem. A lot of these systems, the programming language issue is that they're mostly relying on type systems, and obviously most mainstream programming, we have a legacy support issue that means the type system is not the thing you're going to really change first and foremost in your language. I mean, there's more freedom to do it. GIF taking Java makes sense because you've already got an abstraction over the actual hardware that you're running on, so it kind of gives you an easier place to plug in. But again, that project's been around for a long time, but it hasn't quite grown yet. But I'm hopeful, as I said, seeing the way that the capability operating system stuff is sort of moving, it's growing now. It sort of has been a long time latent, but now seems to be growing. I'm hopeful that will just join up with other information flow controls. Like maybe GIF will become easier to use. Maybe they'll actually try to target porting Java code into an environment that supports information flow control.